Hello everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Abhishek Sinha, and he will be speaking on optimal algorithms for online convex optimization with adversarial constraints. Professor Sinha is a faculty member in TIFR Mumbai. Prior to joining TIFR, he had been on the faculty of the Department of Electrical Engineering at IIT Madras. He received his PhD from MIT, where he was affiliated with the Laboratory for Information and Decision Systems. Thereafter, Professor Sinha worked as a senior engineer at Qualcomm Research, San Diego. He obtained his ME degree in telecommunication engineering from IISc Bangalore and BE degree in electronics and telecommunication engineering from Jadavpur University, Kolkata. He is a recipient of the Google India Research Award 2023, INSA Medal for Young Scientist 2021, Best Paper Awards in Infocom 2018, and MobiHawk 2016, and Jagadish Bose National Science Talent Search Scholarship in 2006. His area of interest include theoretical machine learning, networks, and information theory. Over to you, Professor.
Thanks for the very kind introduction. And good afternoon, everyone. So I would like to thank Professor Anurag Kumar for the kind invitation to present this work. And sorry for the delay. All right, so today we are going to talk about this problem. So let me see. Yeah, it works. So the optimal algorithms for constrained online convex optimization. I'm going to introduce what this means. So this is a joint work with Professor Rahul Bhaze at TIFR. All right. So before we begin, so let's recap what an optimization problem. How do you define an optimization problem in general? So an optimization problem, I'm pretty sure that everyone in this room knows. So what is an optimization problem? So you want to minimize some function over some domain. And if it is a constant optimization problem, maybe you have another constant function. So you'd like to minimize this function f for the set of all g, so for the set of all x that satisfies a constant that g of x is less than equal to j, right? So this is a basic optimization problem. And although, I mean, so it is obvious that what is being assumed? You're assuming that you know both the cost function and the constant function, both f and g, these two things are known, right? So now let's go to the current hot thing, that is machine learning. And how does it relate to the optimization? Okay, so at the very basic level, how does it differ from the optimization is that you would like to minimize some loss. This loss here, this is a random variable. You're taking expectation over this random variable, but you don't know the distribution. So you can't take the expectation, right? So instead what you have sample access of this loss function that you would like to ideally minimize, but you don't have the full distribution yet, right? So there are two principal theoretical paradigms under which this algorithms, machine learning algorithms are designed and analyzed. One is a very classical statistical or the pack learning framework, where we assume the cost functions to be coming from some unknown distribution, but they are IID, right? So this is a statistical pack learning. And there is another like kind of a more general framework. It is called the online learning framework, where you do not presuppose any stochastic distribution, any probabilistic assumption. You do not make any probabilistic assumptions on how these cost functions are generated, and you just assume that they are generated by some adversarial process, right? So there is no distributional assumption. So this is called the online learning framework. So as you can imagine that the second one is more general, it is stronger. And there is a general technique called online to batch conversion, which says that any result, okay, roughly which says that any result that you can prove, especially the regret bound that you can prove in the second setting, that is the online learning setting, that implies a corresponding generalization bound for the classical statistical learning setting, the pack learning setting. So this is indeed more general, and this will be the focus of our talk. So we'll be focusing on this online learning setup. All right. So just to fix ideas and the fixed notation. So let's start by very simple and very classical, the binary classification problem. So what is a binary classification problem? So let's say you have some model, maybe a neural network, and the model weights, these are parameterized by the vector xt. So here I'll be differing from the usual notations that is used in the textbooks. So generally the weights of the neural networks, they are denoted by wt, and xt's are used for feature vector, but for some reasons that will become clear in a second. I'll be denoting the weights by xt and the feature vectors by phi t. So what happens is that when on round t, you get a new sample. New sample means it comes with its own feature vector phi t, and its own label. It's a binary classification problem. So yt could be either +1 or -1. Then what happens? You just feed this feature vector on the left of your model, right? Okay, and then it passes through your network. So it does some magic. At the end, you get some output. The output is some distributions, right? So this is the output. So I'm saying NN means neural network, but it could be any model, right? So this is a probability distribution. So this is supported on two things, that is +1 or -1. What is the probability that your sample phi t is that belongs to either class +1 or either class -1? Right? So this label is now not revealed yet. Now what you do after that? Okay, so this is the prediction of your model. Then you compute the loss. How good your model is, how good your current xt is. You just compute the loss, and the loss is denoted by ft of xt. Right? So ft is a loss function, and you can see that it depends on t because it is a dependent sample. So maybe it is a cross entropy loss. You just compute the cross entropy between the output distribution and the original label, the actual label yt. And you can see that, so it's a function of t, that's a ft depends on the current feature vector and the label, and it depends on xt, that's the current model weights, right? So this is how it works. So important thing to note here is that the loss function ft is determined by the sample phi t and yt. So this is like one-to-one correspondence. And most interestingly, ft is revealed after you select your current model weights xt. Right? So first you determine your xt, and then this loss function is revealed, right? And then what you do in the next round, okay, so the weights you update to xt +1 using some sort of gradient descent, and this process continues. Okay, so this is how, I mean, our typical classification problem is actually, solved in ML framework, or formulated in ML framework. Okay, so now let's, okay, this is just an example. So let's abstract out the essential the features. So this is called the online convex optimization, and which has been studied for the last 25 years. So I'm just going to generalize what we just saw in the last example. So what happens is that you have got multiple rounds. You have got capital T number of rounds. On round one, you first select an action x1, right? X1 could be your model weights, and then the loss function f1 is revealed, and you get a corresponding loss of value of f1 of x1. And similarly, on round t, you select your model weights, you select your action xt, and then the loss function ft is revealed. And accordingly, this process, you update your loss function is your model weights in such a way that it minimizes the cumulative loss function, right? So what is the assumption here? So here is the assumption that I'm going to make. I'm going to assume that the loss function ft is convex for all t, and of course ft is revealed after the action xt is chosen. So this is how this thing actually works. Right? This is called the online convex optimization framework, and it has been studied for the last 25 years or so. All right. So how do you measure the quality of the model? How do you measure the quality of the model that the output by your algorithm? So you are going to you compute a benchmark. So this is called the offline benchmark. This is the benchmark that you cannot compute a priori before seeing all the examples. But after seeing all the examples, you compute the single best action that minimizes the sum of the cumulative losses. So x star is the argmin of sum of ft of x, right? So this is something that you do not know a priori, but at the end you can compute this x star, and this x star is known as a benchmark. So I'm going to compute, or I'm just going to compare the performance of my model, my algorithm, with that x star, right? So the important thing to note is that x star doesn't change with time. X star remains fixed. So all the FTs are changing, but I'm computing a single x star that minimizes the cumulative loss, right? Okay. And so how do you actually measure the performance of an algorithm? So this is called the regret. So you measure, so you first compute the loss of your algorithm. So this is the sum of ft of xt, the cumulative loss of your algorithm. And you also compute the cumulative loss of the fixed benchmark in hindsight, ft of x star. You compute the difference, and this is known as a regret. So of course, you would like to minimize the cumulative loss function. So you'd like to minimize this quantity, the regret, right? So the question is, what is the best bound that you can achieve? Anything sublinear, if you can prove that. So of course, it is by default, if you don't do anything, it is linear, right? Because I'm going to assume the safeties are bounded and stuff. So this is at most, this grows like t. But if it is linear, so if you divide sublinear, if you divide this thing by t, this regret goes to 0, which means that you are learning, right? So the objective is to prove, on a high level objective is to prove a sublinear bound, and the much more refined objective is to show the best regret bound possible. Okay. All right. So as I said, so the first one is A is algorithms loss, this is benchmarks loss, and this is we are competing against a single optimal action. So now you might ask, okay, so this is hopeless, right? Why is it hopeless? Might appear because FTs are revealed in adversarial fashion after XT is chosen. So maybe there is an adversary who is actually looking at what you are doing, and then you're always giving something, something adversarial, so that your model always makes mistakes in terms of binary classification. So why these kind of things are, we were guarded against? The answer lies in the definition of the regret. So although your model, your algorithm can change XT round to round, this X star doesn't change with respect to over round. It remains fixed over all the rounds. So that is why there is a hope that we can actually still prove sublinear regret. And why X star, fixed X star actually makes sense. Think about, so forget about the adversarial setting. Think about, so let's say these FTs are indeed sampled from some distribution. If they are indeed sampled from some fixed distribution, then there is an X star, right? That minimizes this quantity in expectation. So a fixed X star is not a bad benchmark at all, at least in the stochastic setting, right? So that is why it makes sense. And so here is the very basic result, but it showed that a simple policy online gradient descent. Yes, Professor Rajesh. Yeah. So let me okay. So actually I didn't get your question. So you're saying FTs are need not be totally arbitrary. We can compute the gradients of FTs. Yes, but FTs could be adversarial. The gradient. So the function you can compute the once the function FT is revealed, you can compute the gradient at any point. But that doesn't mean that the function FT is stochastic, non-adversarial. No. So FT, so here that was just an example. FT could be a neural network, a convex model, or anything of this sort. Any convex function will be fine. Yes, absolutely arbitrary fashion, just keeping FTs to be convex. So this is only assumption that I'm going to make. So this, as I said, so neural network is a good example. It could be adversarial. For example, let's say you are just training a model and you are using the same sample again and again, right? So let's say you're doing online gradient descent, stochastic gradient descent, but instead of doing it on one pass, you're doing a multiple gradient steps on the same sample. Now it doesn't become an IID model anymore. So it becomes a much more correlated. I do have access to phi t and yt's. So phi t and yt determines the FT in that particular, right? Okay, right. So, but here, okay, just to be specific, yeah. FT is some convex function, any convex function with bounded gradient. Yes, any convex function with bounded gradient. So this is the classical online convex optimization setting. FT is any convex function with a bounded gradient. And it can also be chosen adversarially even after seeing XT. And this regret bound holds these are for any FT, any choice of adversary without making any stochastic assumption. Okay. All right. Okay. Again, this is not working. Oops, what happened? The Zoom stopped working. Okay. All right. Okay. So it might seem magical. Okay. So what kind of algorithms are going to give you this sort of very strong regret guarantee against all adaptive adversary? Turns out it's very simple. Online gradient descent. If you know stochastic gradient descent, this is exactly the same thing as online gradient descent. Only there is no change in the algorithm, only the assumptions, how these functions FTs are generated, this changes. So the online gradient descent, okay, I'm just going to give an example how it actually works. So let's say you are on round T, you have to choose some action for XT. And basically you're trying to minimize this function FT. But this function, yes. Yeah. I only need to know the gradient of FT minus 1. So on round T, the thing that I have access to is FT, everything, all the history up to priority T minus 1. For FT, I have no idea of FT or its gradient. Yes, at xt. The entire function. For now, you can assume that the entire function is presented, but you need only the gradient of ft at xt. But no, I'm actually assuming more. I'm assuming that your entire function ft is revealed. So you can assume that, okay, so let me give you this example. So let's say you're on round t. This is a function ft. This is totally hidden from you. You don't know anything of it. This function, you don't even know its gradient or anything like that. What you know, you're at round t minus 1. You have seen your function ft minus 1, and you know your previous action xt minus 1. So how this online gradient descent work? So you just take a gradient step on ft minus 1, right, of some step size eta t, and that's it. And this is how we compute xt. And you will be evaluated xt, ft of xt, right? So you choose xt, then ft is revealed, and you suffer a loss of ft of xt, right? That's it. And I'm claiming that, okay, so this is a classical result that claims that this gives you, although you don't know ft, a priori, you choose action xt completely, being completely blind to ft, you still have sublinear degrade, order of 50. And what this algorithm uses, it algorithm doesn't even need to know the entire function on every point. It just needs to know the gradient at some chosen point xt minus 1. So it is only a vector is needed, right? But there are some algorithm, for example, FTRL, that does need the full function information. But here, this online gradient descent, it doesn't even utilize that. Does it answer your question? But if you are given f, you can compute the gradient, right? So no, I mean ft of ft, the entire function, ft at the entire, that's what I mean. Yes, yes, yes. Right. So the thing is that these things are structured, these are generally parameterized, as you said. So the only thing that is missing is phi t and yt. So if you supply me with phi t's and yt's, I can compute the entire function, because these are parameterized with respect to phi t and yt. So this is how it actually works in practice. Does it make sense? Okay, okay, all right, all right. Okay, so this is okay. So this is online gradient descent, and this gives you, and if you choose your step size adaptively, if you just appropriately, let's say 1 over root t, then it gives you the optimal degrade bound, order of square root t, right? So this is a classical result of Zinkiewicz, and it came up in 2002 or something. It's pretty interesting. So what we are actually interested in this talk, we are interested in extending this framework with constraints. So this is what we actually mean. So learning with constraints, again, this is not working. So the classical machine learning algorithms, generally they optimize for a single objective function. You would like to minimize the cross entropy, or you want to minimize some L2 square, a norm, and blah, blah, blah. But it is always a single objective function, right? But in modern applications, for example, I'm going to give you some examples. These are multi-objective, almost always multi-objective in nature. It is not just enough to optimize for a single objective function, but you have other constraints that you'd also like to satisfy. So these constraints are also something that you need to learn. So these are also revealed to you as you go, right? So just like your cost function ft, right? So here is an example. So just think about this autonomous driving. So let's say you have an algorithm that minimizes your commute time from your home to your office, right? But if you're this is an autonomous driving, so but this is a Bangalore road, so many people are not following the traffic, or there are also maybe some traffic constraints. So if there are no constraints, then maybe okay, you just commute from your home to your office in let's say 10 minutes or something, right? But you have to satisfy multiple constraints. So you have to satisfy the constraint that you have to at least maintain a safe distance with the pedestrian or the car that is ahead of you, right? And these constraints, you can see, these are not really IID. These are sort of adversarial, and then still you have to make sure that you do not violate these constraints too much. If you violate these constraints, you are going to get traffic penalty. You might also hurt somebody. So this is okay. So this is just a stylistic example of why these constraints actually arise. But there are multiple such applications. For example, AI safety. You would like to classify, let's say, the binary classification problem, but you have to make sure that some safety constraints. So you're not you're being inclusive. You're not excluding some groups, some set of people, or something like that. So it has got application AI safety. Bandit with knapsack. So let's say if you know the classical bandit problem, but let's say I can I can sample the arms, but I also have to maintain, I have to make sure that I satisfy certain budget constraints. So these problems arise in auto bidding problem, right? Where they have certain budget constraints, and based on these budget constraints, you have to pick your arms, or you have to make your bids. Meta learning or multitask learning. So what happens here, you have a foundation model. You're training a foundation model, which means that there will be multiple different tasks that model will be used for. And so these tasks are somehow related among each other. So this task poses a constraint on how we actually train your original foundation model, so that downstream tasks may be processed. The model can be trained downstream such a way that it performs well on all of the possible tasks, right? So this is a meta learning or multitask learning, and it's also it poses some constraints, certain constraints. Another interesting example is wireless scheduling. So let's say you would like to maximize the utility of users, but also have to satisfy certain constraints, throughput constraints to to different users, right? So these are all you're trying to optimize a certain function that is also sort of unknown to you. You learn on the go. And also you have to satisfy certain constraints. These constraints are also adversarial, and you learn it on the go, right? So this is where these sort of problems actually arise. And so let me now take a step back and let's formulate the problem in the language of online convex optimizations. So what changes? So this is okay. So this is how you actually augment the online convex optimization framework by taking into account the new thing, that is the constraints. So just like as before, so you have got multiple rounds. On round one, you select an action x1. Then there is an adversary who gives you two functions. One is a cost function, that's a f1, or let's call it a loss function. And there is a constraint function, g1. So both f1 and g1, they could be adversarial, and they are convex. They are assumed to be convex. And what is the goal of this constraint function, or the role of this constraint function? So g1 represents a constant of the form g1 of x less than equal to 0, right? So if your action already satisfy the constraint, g1 of x1 is less than equal to 0, you're fine. You're not violating any constraint. But if it doesn't, and it will happen because these constant functions are chosen by an adversary, right? So then you will be incurring certain violation. We call the constant violation penalty, and it is given by max of 0 of g1 of x1. So if g1 of x1 is indeed less than 0, the violation is 0. But if g1 of x1 is larger than 0, then you actually incur a penalty, right? And this goes on for every round. And this is okay. And this process goes on. And as I assume that FTs and GTs are convex, and these are revealed after the action XT is chosen. Okay. So as Professor Rajesh said, okay, what is actually being revealed? You assume that only the value of the function and their gradients are revealed. This is the only thing that we know. We need. We don't need to know the entire function. Okay. So, okay, all right. So now we are going to compete. We are going to benchmark against certain action, which is optimal in the long-term basis, which it doesn't change with time. And how are we going to define this this benchmark? So let's consider a single benchmark x star that satisfies all the constraints on every round. So let's say there is so can assume that these are the constraints, and I construct this set S to be the set of all action that satisfies all the constraints on every round. So S consists of all x, such as the GT of x is less than or equal to 0. And this is going to be my benchmark, which means that, and of course, I'm going to assume that S is non-empty. There is at least one action, fixed action, that satisfies all the constraints, and I'm going to benchmark against the best action in this set. All right. So this is a feasible benchmark, and this what is going to be my best action in this set? This is simply the argmin of the cumulative loss in this set is. All right. So single optimal action knowing FTs and GTs. And okay, so now in that case, so previously we were only interested in minimizing the regret, but because of the presence of the GT functions, the constant functions, I am interested right now minimizing the regret as well as controlling the violation. So I would like to minimize this regret FT of x2. This so it was previously there, and I would also like to have a bound, simultaneous bound on the total cumulative violation. All right. Yeah. Variable is xt. No, FTs and GTs are extraneously it is generated. Yes. So x1 is first revealed, x1 is first selected, and then similar to f1, G1 is also, G1 can also depend on X1. Yeah. Okay, so I have not described the algorithm yet. I'm going to describe the algorithm, but it will be clear that you can actually, so we'll be reducing this problem to unconstrained problem, and it will be a combination of FTs and GTs. We'll see that in a second. So I'll come back. So when I describe the algorithm, it will be clear. So I have not described the algorithm for the constraint version yet. So this is the contribution of this talk. Okay. All right. Any question? Any more question? Okay. Okay. So our objective is to control these two things together. So of course, so this is a very fundamental problem. I mean, this is just the online version of the constraint optimization problem, right? So many people have actually worked on this, at least for the last decade or so. And these are some known results. So Soon et al, they had an algorithm quite complicated that gives a regret bound of order of square root t and violation bound of order of t to the power 3 by 4. And then Neely and Yu, so they had an interesting algorithm that has and achieves the optimal regret bound order of root t, but their violation bound is of the order of square root t over lambda, where lambda is known as the Slater's condition. So this denotes the GT of x star. We assume that GT of x star is only less than or equal to 0. So they assume that GT of x star is less than or equal to minus of lambda for all t. So this is the strictly inside. But if you constant violation functions are non-negative, lambda is 0, which means that it gives you a vacuous bound, right? So since this is Slater's condition is unsatisfactory, so the following work actually considered on eliminating this sort of assumptions. And so Guo et al in 2022 in Udif's paper, so they had an algorithm. Again, this required solving a convex optimization problem per round. But anyway, this algorithm has a guarantee of order of root t regret and order of t to the power 3 by 4 constant violation penalty. So the optimal answer was not known. So it was not known even what is the best cumulative constant violation that you can achieve while maintaining the order of root t regret. So Soon and Go, okay, so their algorithm was a little bit, so Soon's algorithm is Bregman divergence. Again, it needs to know the entire function. So the algorithmically, it's only better, but not in terms of the guarantees. So it is easy to implement, but not in terms of guarantee. So E et al, it somehow just improved. It is parameterized. So they had an algorithm that achieves order of t to the power max of beta 1 minus beta. Beta is a tunable parameter and violation of t to the power 1 minus beta by 2. But if you want to achieve, you want to maintain the optimal regret guarantee, so you have to put beta equal to half. That gives the same result as Go, t to the power 3 by 4. So this was a state of the art even in 1 year or 2 years back. Right. So as I said, so this is t to the power 3 by 4. So the question was, the open question was, what are the fundamental limits? What is the best thing that you can actually achieve in this model, in this problem? And especially, is it possible to simultaneously achieve order of root t regret and order of root t violation? And whether this is achievable and whether there exists a lower bound to that. So these problems are totally open. So yeah. Yeah. Just a second. Lambda is a problem dependent parameter. So if you change, so for example, let's say all your GTs, so here we are only looking at the hard constant. Hard constant means max of 0 GT of x t. So this is how we actually define. So these are always non-negative. So in that case, lambda is going to be equal to 0. Lambda is going to be equal to 0 because it requires GT of x star to satisfy minus of lambda, right? And lambda is a non-negative number. So in that case, P, the violation P becomes vacuous in their bound. So they are looking for soft constraints where there is cancellation, but we are looking at the hard constraint part. This lambda is going to be problem dependent, and even in this particular setting, lambda is going to be equal to 0 in our case. So so here you will take a look at the definition of the constant violation. So let's say this is called a hard constant violation, where it is a max of 0 GT of xt. You can also define another soft constant violation where you get rid of this max operator inside. So your constant violation is simply going to be sum of GT of xt. In that case, it makes sense that GT of x star to satisfy minus of lambda. because this quantity can never be less than equal to minus of lambda for any lambda positive. So they were actually considering this something called the soft constraint violation, and they assumed that there exists some extent that makes that each of these individual constant violation to be less than equal to minus lambda, where lambda is some constant that depends on the problem specific constant. So it is not uniform bound. It is a problem specific bound. So what I'm claiming is that even in our setting, lambda is actually 0. So their bound is vacuous. So that is why the following work they concentrated on eliminating the so-called Slater condition assumption. So there is no Slater. Lambda could be equal to 0. So GT of extra could be 0. Order of root is fine, right? Oh, the constants only G and D. So these are G is a uniform upper bound to the gradients of FTs, and D is the diameter of the set. So I'm going to give you, I'm probably going to show you the full expression. So it doesn't depend on FTs and GTs at all. It only depends on the uniform upper bound on these FTs and GTs, on the gradients of FTs and GTs. Yeah, so these constants are really constants. Okay. Yeah, but in addition to that, they had one of a lambda dependence, and lambda is a problem specific. But and what I'm saying is that in this setting, lambda is 0, so this gives a vacuous bound. Yeah. Yes, we'll be coming to that. We'll be coming to that, but not in this particular problem, but I'll be coming to that. We'll be seeing a curve that R and P is going to satisfy. But this is towards the end of this talk. So here I'm claiming that you can achieve both square root T unconditional. And this is optimal. You can't do better without making any additional assumption. But if you make some additional assumption, for example, smoothness, you can indeed get better CCV bound. But this is probably close to the end of the talk, and if I'm not given additional time, I'll probably not have time to cover this result. Okay. Yeah. The fundamental, this is a very good question. The fundamental difference between CCV and regret being that the offline optimal, you have an upper bound to the offline optimal for the CCV. You know what is to target for. So GT of X star, sum of GT of X star is less than equal to 0. So this is 0 is your target. But in regret, there is no upper bound, there is no target for it. And that makes controlling regret much more difficult than controlling the violation. And that will also show up in the bound that we derive. Right? So this is a very good question. So you know the target there, here you don't know the target. So that is okay. Oh, but anyway, we can take it offline. But okay, all right. So that was an open question, and our main contribution is that we actually proved that there is an algorithm, very simple algorithm. I'm going to describe this algorithm, and unconditional, without making any sort of Slater condition assumption, it achieves square root regret and square root violation. Not only that, this is a tight result. You can't do better than that without, no algorithm can do better than that, either on regret or on CCV without making any additional assumption. So this is unconditional tight result, and this result is actually surprising. It was shocking to the community because previously there was an ICML 2019 paper that actually sort of conjectured that this result is not possible. Square root T violation you can't achieve with square root T regret without making any additional assumption, especially stated assumption. So this was their thing. So on the other hand, the point square root T achieved by Nili and you, there is a divided by lambda here. For k equal to 1 is not part of our achievable guarantees. We attribute this gap to the strictest Slater assumption. But here we are going to show that this is really not required, and you can actually achieve this. We disprove this conjecture with an algorithm that I'm going to describe. Okay. The algorithm is very simple. So it is a black box reduction. I'll be going to reduce this problem, the COCO problem, to the standard OCA problem without any constraint. And then I'll be simply running an AdaGrad on some loss function that I'm going to constrain. Okay, so this is that's it. This is the algorithm. So this is simpler, cleaner, and modular approach. And not only that, it replaces the previous we used some sort of primal dual based technique, and they achieved optus. But we totally get rid of this sort of primal dual approach. Our algorithm is totally primal algorithm. Okay. So the algorithm, the question is how to train your model for both objective when you have both an objective function and a constant function. So here is the algorithm. You just compute the the violation, the CCV that you have incurred up to round t. So this is your QT, right? And then you form a surrogate function. It's very intuitive. So you have to balance between these FTs and GTs. The question is, what is the right weighing factor? FTs and GTs are definitely not comparable. So you have to make them comparable by multiplying this GT by something, or equivalently FT by something, right? What is the right weighing factor? So this is a phi dash of QT. I'm going to explain what it is. So phi is an exponential function. It is known as a potential function in Lyapunov function, and QT is simply your current violation. And I claim that if you choose your phi appropriately, this gives you the option. Okay. And once you do this, so as I said, this is a time heading algorithm dependent way. Okay. And phi is a convex function, this is a Lyapunov function. And you just now think of this as an OCO problem, online convex sublimation problem, standard OCO problem without any constant, and run any no-degrade algorithm on if you had P of X. The only complication here is that why you can't run an online gradient descent as a black box, because of the presence of phi dash of QT. Because you see QT is time varying and it depends on, it evolves as algorithm progresses. You don't have any direct control over QT, but this online gradient descent algorithms, they need a strict upper bound on all the functions that you're going to see. So that's why constant step size sequence is not going to work. You need something called adaptive step size sequences, but this is something that is well studied in online learning literature, and AdaGrad is one such algorithm that can handle that, and we are going to use this. So here is the algorithm. This online gradient descent, you make a projection if it goes beyond this at X, but that's not very important. And in practice, they never do this projection anyway. So this is the adaptive steps of iterative because no a priori bound with details to FTI. Okay. So what I'm actually going to do next, I'm going to give a very quick proof steps. And as I said, I mean, the proof is actually 3 lines. The previous paper had more than 5-6 pages of proof proving these suboptimal bounds, but here a proof is only 3 lines. So that's why I just wanted to give you a glimpse of how this technique actually proof technique works. And I believe it is absolutely new. So this has not been done before. Okay, so the convexity of phi, I assume the function. So choose any convex Lyapunov function. So what is the basic property of convexity? It is upper bounded by the Taylor series, right? So phi of Qt is upper bounded by phi of Qt minus 1 plus phi dash Qt. Just expand this, the first order Taylor series. And this Qt minus 1, so this is a linear term, and this is simply your GT of xt plus, right? So this is a new violation. So this quantity, phi of Qt minus phi of Qt minus 1, this is known as a change in potential, the drift in Lyapunov theory. So your drift is upper bounded by something phi dash of Qt multiplied by GT of xt. Fine. Okay. And now, just recapitulate the feasibility assumption. What is our benchmark is going to satisfy? Our benchmark is going to satisfy all the constraints simultaneously, right? So in particular, I have GT of x star equal to 0, max of GT of x star equal to 0 for all. There will be a max for here. Okay. So what I now next do? So I previously derived this drift, the change in Lyapunov. Now I'm just going to add this 0 on the right hand side. Okay. So this is a drift. And now there is a philosophy called the drift plus penalty. So I have already got a bound on the drift. I now just need to add the penalty. And what is my penalty on round t? It is simply going to be ft of x. This is my penalty. So I'm just going to add this ft of x, and ft of x star is some constant. This is the penalty of the benchmark. I'm going to add these two quantities on both sides. Okay, that's it. Now you just sum it up. Once you sum it up, you can see that this is telescoping. So phi of Qt minus phi of Qt minus 1, the telescopes, and at the end you get a equation. We call this is the fundamental contribution. So this is called regret decomposition inequality. So we derive something called the regret decomposition inequality. Interestingly, so this is a change in the potential from round 0 to round t. This is a regret of your original function. And the right hand side, interestingly, the way we have defined this this surrogate function, this is simply the regret. If you see this is simply the regret of the surrogate function. So change in potential plus regret of original function is upper bounded by the regret of the surrogate function. So if you can control the right hand side, you can control the sum of these two. And I'll also be arguing that controlling the sum of these two is individual bound for both of them. So that's it. And so you're almost here. So we run a no regret policy. But as I told you earlier, there is one issue I can't use OGD because of the changing, the gradient is changing. But anyway, I can use the AdaGrad. So adaptive step sizes. So here is the known regret bound for AdaGrad policy. So let's say I've got multiple functions ft's with this gradient given by gt. Then if you choose your step size sequence adaptively, which depends on all the past upper bound and the gradients, your regret is upper bound equal square root of the sum of the square of the gradient. So this is known by result by Ducci. It was proved by Ducci in 2012. So quite famous result. So I'm going to use this result. And so now, okay, so now what is about by this quantity? So from getting using the regret bound from here to here, what I have used, I have only used the monotonicity of the Q sequence, that is the violation sequence, because it can only add up, it can only increase, and this gives the corresponding bound. Now, interestingly, you can see that on the left hand side, I've got phi, on the right hand side, I've got a phi dash. And the question is, with this result, can I get a bound on both regret and Q for an appropriate choice of phi? And I also have not mentioned what the appropriate choice of phi is going to be, but you can guess. So somehow I have to make this phi to be almost equivalent to phi dash of Q. I need to cancel this out. So what is the function that makes phi equal to some constant time phi dash? The exponential function, right? So just choose an exponential function, and with this, this exponential times something, some constant that you choose accordingly. And this is a functional inequality solved. It is not very difficult to solve. I mean, you can solve it with +2 level algebra, right? But in general, these inequalities are called discrete Grunwald type inequalities. This could be really hard to solve if it is a nonlinear, but fortunately, this was not the case here. If you know, I mean, it's just +2 level math, but it just needs some thought. Okay, and that's it. And by solving this, it just takes 2 lines and it prove root t regret and root t log t CCP. And actually, this log t is not necessary. So somebody after the publication of our paper, they also removed this log t factor by changing the algorithm. So square root t is actually achieved. Okay. So remarks on our approach. So the main idea is regret decomposition inequality. I believe it is a very powerful. And so what you are actually going to do, so this is the function, the right hand side is actually a function of qt. So this is a functional inequality. And you want to solve this functional inequality with a appropriate choice for phi for weighing the violation. And we can use a full part of adaptive regret bound for OCU. We don't need to look under the hood of the OCU algorithms. We can just use end-to-end regret bounds, and that's it. Okay, so this is the strength of this approach. There is no prime algebra, nothing going on. We are just using this thing with the black box. Okay, and the complexity of our algorithm, as I said, it is significantly less than prior work. Why? We are not executing any context optimization step on every round. The previous algorithms, as Professor Rajesh mentioned, do I need to see GT? They actually needed to see the entire GT because they had to optimize this some function of GT plus something over the entire domain. So this requires the knowledge of the entire GT, but here for us, only the gradient information is enough. So no convex optimization is executed. Okay, what about the lower bound? I'm going to skip this for because I'm just running out of time. It is a beautiful proof technique, and it shows that square root t, you can't do better than square root t regret. We know even unconditional you can't do better than square root t, but even violation, if t is larger than or equal to t, you can't even do better than square root t in terms of violation. But only under the condition that it is a high dimensional problem. That is when your dimension is actually larger than or equal to t. So I'm going to skip it, but because we just lost some time, because I just wanted to get one last result. So this is a very new result that is actually uploaded in this archive a few weeks back. So story so far is order of root t regret and order of root t CCV, and the bounds are tight for d greater than or equal to t. The question is, can we do better? Of course, you can't do better if you don't put any assumption, because that's what our lower bound said. So what kind of assumptions you can make? So maybe you can make 2 sorts of assumptions. Maybe just assume d to be a constant. You are working on a constant dimension set, or you can assume these functions are somehow nice in the sense that they are, let's say, they are smooth. In that case, very surprisingly, you can actually even reduce the constant violation even smaller, right? This is even smaller. So the regret is anyway lower bounded order of root, even for unconditional unconstant problem. So there is no hope that you can reduce it. So the question is, can we achieve a smaller CCV by trading it off with regret? So now I'm coming back to your question. So is there a trade-off between this regret and CCV? And indeed, turns out to be yes. So there is a trade-off, and this goes like this. So fix any user-specified parameter beta include in this interval 0, 1 closed interval. Then there exists an algorithm that achieves square root of dt plus t to the power beta regret and d times t to the power 1 minus beta CCB for any d-dimensional bounded diffusion set. So if you set beta to be something larger than half, you're increasing your regrets because this is a dominant term. And so you get a regret of the form t to the power beta, but your CCB gets reduces to t to the power 1 minus beta. The product of these two is actually being upper bounded by order of t. So this is the curve that we actually get, right? So this is the regret. This is achievable. So anything greater than square root t, but the CCV can be very small of the order of log, right? And these results imply that CCV can be made, indeed it can be made as small as the order of log t. The proof idea is almost the same. You start with the regret decomposition inequality, but now you exploit the fact this x is not some arbitrary point. X is something that satisfies all your constraints. And that gives you, and with this you can actually achieve even smaller regret, something called the small loss bound. But the losses are, the regret is not even a function of square root t. The regret is actually given by the square root of the loss of the benchmark. So use this sort of bounds, and this gives you the corresponding results. So here are some simulations that shows the variation of the regret and CCV with beta. So indeed we see that if you increase your beta, the regret increases, but the violation decreases, right? For any beta larger than or equal to half, you can see that rate. So some area research here that we're currently working on. We're currently working on constraint RL setting, constraint RL problems. How can actually use this ideas for reinforcement learning problems where you have states in addition, constraint non-convex optimization, especially DR submodular function. How to do this thing with bandit feedback when you don't even have the gradient feedback, you only know the value of this function. That's it. So you have to estimate your gradients. So this is bandit feedback and also projection-free algorithms. So can you actually avoid the projection state that are inherent in this sort of online gradient descent algorithms for some nice structured decision sets? For example, can we just do linear programming about that? So some final remarks. So COCO is a fundamental problem of current interest. It models important problems with constraints or multiple objectives. For example, multitask learning. The result actually solves a decade-long movement problem. And for strongly convex cost, we have many more results. I'm just mentioning one. We can get actually logarithmic regret bounds. And not only that, the uniform feasibility assumption can be dropped. This is somewhat technical, but it is not necessary that xstat satisfies all the constraints or every time. It is also, our results also holds if xstat only satisfies a long-term constant. So sum of GT of xstat is less than equal to t. Even in that setting, you can achieve similarly. So with this, I would like to conclude this talk, and let me know if you have any questions. Yeah, so here our objective was to get the best bound possible, but not so in terms of the practical performance. So we have not actually tested with Adam, but I believe that if you are using it something like similar to AdaGrad, Adam uses a one momentum term, but momentum term is theoretically not needed, but it might give you some edge in practice. So we have not actually experimented with that, but theoretically speaking, Adam cannot improve the regret or the violation. Yeah, but in practice, it might have some. Yeah. Yeah, that's an interesting question. So maybe you can answer the question. Yeah, almost. Yeah, the square root is square root t. We actually showed that it actually holds. Yep. Okay. Yes, yes, right. Blackwell's approximability. Yeah. Right, right. Yes. Right, right. Mm-hmm. Right, right, right. Yes. Best policies, yes. Yep. Root T, okay. Root T, yeah. Mm-hmm. Yeah, yeah. So Blackwell's approachability, it was shown by Abhishek that Blackwell's approachability is equivalent to online convex optimization. So it was shown in 2012 by Professor Abhishek, Jacob Abhishek from UC Berkeley, I suppose. So the result is online convex optimization and Blackwell's approachability, they can be mapped one-to-one fashion. So any result that you can prove with Blackwell's approachability, they can also prove via OCO and vice versa. So OCO, in fact, is more stronger than Blackwell's approachability. So it was, there is a nice result. So yes, so I think you are looking for some Blackwell's approachability type algorithms, right? Distance from the boundary, right, right. Yeah, so this is actually studied also in the theoretical computer science literature. This is called convex body chasing problem. The convex body chasing problem. So you have shown some sets, and you want to, but you are always one step behind, right? And you want to approach this convex set in such a way that you minimize the total distances. So let's say the distance to the sets. And so Rahul is actually, yeah, so there's an interesting connection, this convex body chasing, but there's no one-to-one mapping. So they used some very I should say inefficient algorithm. These are not gradient based algorithms. These are used something called I think what kind of algorithms? So one is called the center of gravity based method, but this is center of gravity is very difficult to compute even for a convex body. But here we are looking for efficient algorithms. But not only that, even from the fundamental regret point of view, we have not found the direct connection yet between the convex body chasing and this COCO problem. But these two are very related, and I'll definitely check out Shinkin's work. But there are multiple works on multi-objective sequential optimization. Uh-huh.